And now we are going to add complexity. We have limited our mathematics up till now in both limits and in derivatives to just polynomial functions, x squareds, and we've included square roots, but almost everything with just a regular function that can have a power. Now we're going to go to new functions, trig functions. So first of all, we're going to look at the graphs and see what happens with our graphs. We'll start with sine. There you go. You can add those words in if you like. Apparently, the derivative of sine is cosine, and the derivative of cosine is negative sine. Wonderful. Wonderful that they're so close and easy to forget. Easy to mix up. So we're going to try to develop a logical way so that you can remember that one is positive and one is negative. And in the end, what I like to use as a memorization strategy to remember this is I focus on the first one. The derivative of sine is positive cos. And then everything else can be figured out from there. All right, so GeoGebra, here we go. Here is my graph of sine. Does it make sense that the slope of this line, the way that it's drawn, there's a tangent right at 0. It looks like a perfect diagonal line, which would be a slope of 1, y equals x. That's a starting point. So that kind of explains why it's cos. And as I move up from right to left, does it make sense that my tangent slope would be positive? And one of the things that's going to be really helpful for you mental math-wise is to sort of visualize a tangent on a graph and whether its slope is positive or negative. In this case, since its slope is positive in the first part, it makes sense that the derivative, if it's going to be cos, the derivative of sine is going to be cos. Look how beautiful that is. It's just, there we go. It really is beautiful that as you graph every single tangent along the way, the slope works out perfectly to make the cos graph as you're going. It's sort of like a marvel of mathematical nature. And since right here at the beginning, your slopes are all positive, it makes sense that your sine derivative is positive cos. Can you see that as a way that can help you remember that the derivative of sine is positive cos? And if we pull up our graph of cosine, if we pull up our graph of cosine, do you see it? If you immediately move your tangent to the right, wow, here we go, let's try it again, that your slopes are negative to begin with. And the only way that can happen is if your sine graph is a negative sine graph. Oh, so pretty. So if you think of the derivative as giving you equations of your tangents' slopes, equations of the slopes of your tangents, and you can see from your cos graph that right away your tangent lines will be negative. The only way that's possible is if your sine graph goes into 0. It also should start to make sense for you that whenever you have a maximum or a minimum graph, a maximum or a minimum on a graph, does it make sense that the tangent is always flat? Okay? And there you have the biggest application of calculus that there can be. Flat tangents. Okay? Like, calculus is so powerful, and yet when you break it down, all it is slopes. And it's really important when the slope is flat. There is calculus. And why? Well, as I mentioned before, so much of our life is trying to find maximums and minimums of stuff. Optimizations. Making as much money as you can. Saving as much money as you can. Using the least amount of materials to make something as big as possible. We'll get there. Oh, I know you could get me off topic and I could start teaching it right now, but we have to build our mathematics slowly, right? If we wanted to maximize, for example, volume, right? Drinks are sold in volumes. That would be a place where you could save money if you made the shape perfect to use the least amount of material, okay? Then, I mean, you want to make $1 million? If you could figure out a way that Coca-Cola could save 0.1 cents per bottle, plastic bottle, or per can, do you know how much money they would make? They could pay $1 million for that technology, and they would still be making money off the result of you saving 0.1 cent per thing. Question? Well, you got to be careful when you're thinking about tan, because tangent, in that sense of the word, tangent is on a triangle, your opposite over adjacent. And here we're using a different definition of tangent, a tangent to a curve, meaning you're drawing a line that's touching it only once. The value of the slope is not equal to the value of the tangent function. For which graph? So here, my slope is negative in quadrant 1 for a cos graph, but in quadrant 1 for my sine graph, but one of them is positive, one of them is negative. I'm not sure I follow. I bet you they do. Right? Mm-hmm. Yeah. I got a math book for Christmas, and it has a bunch of mathematical, I know, embarrassing, right? But it's really good. It's called Humble Pie, if you want to write it down. It's an international bestseller. Like, to hit international bestseller for any book is amazing. The fact that this one's topic was math, and it's still, like, there's not too many of us out here that like math books, right? So to hit an international bestseller. Anyways, in that book, they talk about mathematical errors, and one of them happened with Pepsi. When I was growing up, Pepsi had a promotion on where every Pepsi you bought, you could take out the liner inside the bottle, and it had Pepsi points. And you could collect these Pepsi points to get prizes. You could collect enough for a t-shirt. I collected enough because I went to the golf course, took all the Pepsi points out of the garbage and everything. I had collected so many Pepsi points. I got a Pepsi watch. Came in a very nice Pepsi silver container, everything. Super exciting, okay? They made an advertisement on TV saying, this is how many points for a t-shirt, this is how many points for a watch. And then, at the end of the ad, they put, and if you have 20 million points, you can fly your own fighter jet to school. And they show this kid who gets into his fighter jet and flies to school. Okay? Now, Pepsi made a little mathematical error. Okay, well, Pepsi made a mathematical error. They put on the TV ad a huge, insane amount of points that presumably would be impossible to get, okay? Because you couldn't buy that much Pepsi. However, Pepsi then added a thing to their Pepsi points that you could still get your watch if you were short points and paid for the extra points. Okay? So now you could buy points. So theoretically, you could buy enough points for the fighter jet. And they miscalculated because the fighter jet was worth $25 million, but it only cost you about $7 million to buy the points. So one guy did. And there was a huge lawsuit.
You don't actually get the fighter jet, right? Or
Well, he was supposed to.
is he supposed to actually get ownership of it?
Yes.
Okay. You just said take it to school.
Well, no, but that was like, if you owned it, then you could take it to school, right? So it was a huge legal battle for Pepsi because common sense, when you watch the ad, was the amount of points for the fighter jet was really a joke. But Pepsi had to prove in court that it was a joke. Even though they had, and the other guy was arguing, well, they used the same style when they talk about the watch, and the watch wasn't a joke. They used the same style when they talked about the other prizes. Then they just led into it. So Pepsi won the battle, the legal battle, but it was, they then reissued the ad with a higher amount of points. Yeah, they would have had to do that, but I'm sure.
He had $7 million worth of Pepsi points that he can't spend on his money anymore. He's gonna get
Yeah, it was like, I'm going to spend $7 million and get that many T-shirts?
Yeah.
That would kind of suck. Anyways, so stories like this, you can see, okay, yeah, it's actually a fascinating book. Sorry. Back to our math. So there we've seen our graphs of why the derivative of sine is positive cos, the derivative of cos is negative sine. Question? Yes, but that'll be in our next unit when we're learning how to graph applications. So now, all of the rules that you've learned so far, we can throw trig stuff into them.
Oh no.
Oh, yes.
Oh no.
Oh, yes.
God no.
Oh, yes. Okay, all right. And you have to determine with your trig functions, your brain is going to have to, like with the chain rule, this is a chain rule, your brain is going to have to determine what's the inside function, what's the outside function. Here we have sine 4 of x. Mathematicians don't like brackets, but for all intents and purposes, in this one, you might like to, you know that this means the same as this? But mathematicians put the 4 on the inside. So if you want to rewrite it like this, can you see that the sine x function is on the inside? And the power of 4 is the outside. So we have a chain rule. What does a chain rule look like? 4 would come out in front. Keep the inside the same. Then multiply by the derivative of the inside. And is the derivative of sine positive cos or negative cos? Positive cos. So technically, if the answer was written in proper notation, and here I could have all sorts of fun with a show that question. When I say fun, people start shaking their heads, right? Because that's when I have fun. That's when you make things complicated, Mr. Chair. Yeah, I'm sorry. Can anybody see that this is equal to Can you see how I did that?
To be honest with you, no.
Good. You're not there. You haven't done identities yet. I have the identities formula up on the wall over here. Here's a formula from grade 12 pre-calculus. Sine 2x is equal to 2 sine x cos x. Having that in your head, can you see how I went from here to here? If I took out a 2, a sine x, and a cos x and rewrote it as this, what would I be left with? I'd still be left with a 2. I'd still be left with sine squared. Agreed? So we can play. Now, the show that questions are very similar to identities questions even more because we start using our trig identities in a show that question. Here. I'll do a preliminary step. Not good? Very good. Yes? No. This was just me playing around. The right answer would be this one, not simplified. Okay? Either in this form or this form, either is fine. But just opening up your mind that as soon as you have something that you can play with, feel free to play with it. And that's how, things like that is how math contest questions are made. They find a place where they can play with something. They manipulate it so that when you see the question, it doesn't match something you're familiar with. And if you can see the connection of how to switch things around, it makes it easy. We have another chain rule here. But this time, what's inside is the 3x cubed is inside the cos. Can you see the inside function? And one inside the other. Do we have to do a product rule because we have a 4? No. We only do a product rule when we have variables in the products. The 4 is just a coefficient. It's going to stay a coefficient and not affect things. But as far as our headspace goes, we really have to know our product rule, quotient rule, chain rule super well to manage it with the data that we're given. Yes? Yes. You could do the product rule, but if you did the product rule here, which is a good point, when you do the derivative of the first one, you just get 0, which is sort of like, oh, I didn't need to do the product rule. I just did extra work to show something multiplied by 0. Okay, so y prime. If it's a chain rule, we do the derivative of the outside function first. The outside function is cos. What's the derivative of cos? Negative sine. So we would have negative 4 sine. Keep the inside the same. Calculus is also a study of restraint. The keeping the inside the same is the hardest thing for students. And then you multiply by the derivative of the inside function. This is my inside function, 9x squared. As far as writing this, if you would simplify this in the end, you would write negative 36x squared sine 3x cubed. Whoops. I forgot my little dash. There we go. They are one-step questions that involve a lot of brain power. You have to hold everything in place. You have to recognize what's an inside function, what's an outside function. Okay? Yes. Right? We have a y that's not by itself. So then you have to do implicit differentiation. And on the right-hand side, do you see that you have a product rule? So here we have our product rule. And on the left side, we have implicit differentiation, which is a chain rule. How do you do implicit differentiation? So we take the derivative of both sides. The derivative of sine y, the y is inside of sine. So how do you do it? That's a chain rule. The derivative of sine is cos. Keep the inside the same. Multiply by the derivative of the inside, which is your derivative. Equals. I should have left. I do get so big to begin with. I need to leave space. Right-hand side is going to be a product rule. How do I do a product rule? I keep one the same. Multiply by the derivative of the second one. The derivative of cos, I'll put that in brackets because it's negative sine. If I didn't put it in brackets, it would sure look like I had subtract sine. Plus, keep the second one the same, multiply by the derivative of the first one. So I really need you to have your, like the product rule, quotient rule, chain rule. They have to be memorized so well that you can just use them and be able to use them in a bunch of different contexts and when they get put together. Now, if I want to find dy dx, I can get that by itself. By dividing both sides by cos y. If you check this answer in your answer key, they'd probably multiply the negative times the 3. They would probably look and say, hey, between these two terms, you can factor out a 3x to the 6. And they would write it in factored form. But for us, for now, this would be fine, because the question didn't ask us to simplify. It wasn't to show that question. We just needed to get dy dx by itself, and we have done that. So basically, by adding a derivative of a new function, like we just learned sine and cos, you now can do all the other derivative things you've done with this new knowledge. And that's what we're going to be doing over the next couple of days, just adding new derivatives as we go. Here's a show that question. If f of x is sine x cos x, could you show that it's equal to cos 2x? So first, I'd like you to find the first derivative on its own. Where's your notes booklet? On the table at home. Okay. All right, how did you do finding your derivative first with the, right? There's our derivative with the product rule. Keep one the same, derivative of the second, plus keep the second the same, derivative of the first. Remembering that that negative goes with the derivative of cos, and the derivative of sine is positive cos. You could now rewrite this as cos squared x minus sine squared x. And if you haven't learned the formulas yet, because you haven't done identities, they're all up here on the board. So you can, and those, I don't cover those for tests or what else. So those formulas are available. It's more than just, yes. So cos 2 alpha has more than one. But one of them happens to be cos squared minus sine squared, so then you can just change it to cos 2x. And you're done. Okay, try that. Okay, let's see how you did on the first one here. Did you see that it was a chain rule? Derivative of the outside function is the cos. That would give you your negative sine. Keep the inside the same. Again, there's your restraint factor in calculus. You kept the inside the same. Multiply by the derivative of the inside. It's a chain rule because we have a function inside of another function. You can do the derivative of cos x. That becomes negative sine, but the inside also has a derivative, so then we have to do the chain rule. Have fun with the next one. No. Quotient rule. Quotient rule with chain rule inside. There'll be a chain rule with this one when you do its derivative. There'll be a chain rule with this one when you do its derivative. And you have to use the quotient rule as your overall structure.
Wait, is there supposed to be a bracket right here?
Yeah.
So it's two, like that's chain and then that's code. That's like
There'll be chain rules for both of them. But you have to be careful because you started doing the derivative of the inside, but you have to follow your rules. We have to do quotient rules first, and then do the rules going along as you're working with your quotient rule.
well, like I did this part first.
Yeah.
It to negative x.
So you can change, you can rewrite this as cos 3x over sine x to the negative 1/2.
I did hide that.
Right. But it needs to be, then, now that it's set up, now you can do the derivative. Okay, let's see this next one. First of all, for the setup, take your time to change the x to negative 1/2. Because the square root would be x to the half. The fact that it's on the bottom, change it to a negative 1/2. Now, we are going to do the quotient rule with this. What does the quotient rule say? Keep the bottom the same, multiply by the derivative of the top. In the derivative of the top, you have the chain rule, because there is a 3x inside of cos. The outside function is cos, so the derivative of cos is negative sine. Keep the inside function the same, then multiply by the derivative of the inside function. Now back to your quotient rule, where were we? We now have to subtract. Keep the top the same, that's why the cos 3x is there, then the derivative of the bottom. The derivative of the bottom is a chain rule. The outside function is sine. The derivative of sine is positive cos. Keep the inside the same, then multiply by the derivative of the inside function. Now back to your quotient rule. We've done the top of our quotient rule. We take the bottom of our quotient rule and say keep the bottom the same and square it. So what makes these difficult is you have to have your quotient rule steps set up and keep your other rules set up along the way. I don't know if this would That's your quotient rule in words, right? This is what we keep saying over and over again. So what happens as I'm going along? I keep the top, I kept the bottom the same. I can maybe, if I wrote this out in words, I'd maybe go, check mark, I've done that. Then what do I have to do next? I have to do the derivative of the top. I look at the top and I'm like, oh, I have to do the chain rule. Make a little note here. This was a chain rule. And this is where you can get lost because the chain rule is hard on its own, right? You're thinking about what's the outside function, what's the inside function. And you get done this, and you might forget where you are in your quotient rule steps. Does that make sense how this gets difficult? Because with lots of practice, I can keep all of these things in my head because I've had lots of practice. It's very easy for you without the lots of practice to get mixed up or lost along the way because it requires a lot of focus. So once I do this chain rule, I have to come back to here. Okay, what did I just do? I just did that. Where am I at? Oh, I need to write a minus sign, okay? Keep the top the same. I like these ones that's the things stay the same. Life is so good when you can just like, it's a break. I just have to rewrite the top. Then I have to do the derivative of the bottom. Oh, the bottom is another chain rule. This whole part here is another chain rule. So then I get bogged down in that focus of where I'm at. Finally, I get that derivative done. I can say I've now done this. Where am I at in my quotient rule? I have to do the bottom squared. Again, that's fairly easy. You just take your bottom, put brackets around it, and square it. But in the end, we can write our answer all in one step. So that is a positive in that sense. Oh, I really want to do a couple more. We haven't got to a double chain rule yet. Looking forward to the double chain rule. The next formula that you're given is that the derivative of tan is secant squared. But we're going to pretend we don't get that formula, and we have to prove it. Or deduce it. How could you do that? You don't know the derivative of tan, and we're supposed to show that the derivative is equal to something. Yeah. Switch it. Switch it to sine over cos. And then you have quotient rule. What's our quotient rule say? Keep the bottom the same. Derivative of the top. Minus keep the top the same. Derivative of the bottom over the bottom squared. Okay? And now that we've found the derivative, now I get playtime. It's an identity. Can you rearrange this to make it secant squared? Well, if you multiply out the top, are you okay that I write the top as cos squared x plus sine squared x? And that means the top is equal to 1. So then it's 1 over cos squared. And 1 over cos squared is equal to secant squared. For those of you in pre-calculus, you've done that sine squared plus cos squared equals 1? Yes, yes. So then that is the step for figuring out this one. Oh, okay. Yeah, so what we did is we changed tan to be sine over cos, and then that makes it a quotient rule 1. And since we know the derivatives of sine and cos already, we can figure out the derivative of tan. Which you wouldn't. you, your brain has to be able to like, just, yeah.